Welcome to This Explainer. Today, we're diving into a real cosmic detective story. We're going to unravel a massive mystery centered around a rebellious little galaxy known as Caldwell 51. You know, our understanding of how galaxies form is constantly being tested by new data. And today, well, we are looking at a fascinating outlier that literally throws the rulebook out the window.
But before we get into the heavy astrophysics, I really want you to ask yourself a question. How could a single tiny dwarf galaxy, one that's actually moving against the flow of the expanding universe, completely upend our standard understanding of cosmic history? I mean, it sounds a bit like science fiction, right? But the data we're about to explore is very real, and it exposes a major flaw in how we model the early universe. 2.45 million. That is the staggering distance in light years from Earth to our subject. It's hanging out way out there in the Cetus constellation, situated right on the absolute very edge of our local group of galaxies.
Okay, let's set the scene with some quick vitals about this galactic rebel. So Caldwell 51, which astronomers also call IC 1613, was first discovered by Max Wolf way back in 1906. It's what we call a dwarf irregular galaxy. So it doesn't have those grand sweeping spiral arms like our Milky Way, but honestly, its most unique feature? It's blue-shifted. It is hurtling right toward us at 90 kilometers per second instead of expanding away. And crucially, it's highly isolated, meaning it hasn't had any recent violent run-ins with massive galaxies to strip away its gas.
Let's dive right into the evidence. The Hubble Space Telescope pointed its Advanced Camera for Surveys, or ACS, at a very specific footprint just inside the half-light radius of Caldwell 51. Basically, this precise positioning gave astronomers the perfect representative sample of the galaxy's stars, completely avoiding the crowded mess you'd get if you looked directly at the center.
Section 1. The overcooling problem, a theoretical flaw. So, to understand why Caldwell 51 is such a big deal, we first need to understand the massive cosmological conflict at the heart of today's explainer. Our standard computer models suffer from this thing called the overcooling problem. In these models, small galaxies are basically expected to burn through their gas and form almost all their stars right at the very beginning of time. Essentially, the models predict a huge early spike of star formation, leaving these dwarf galaxies completely starved of gas in the present day.
Section 2. Reading stellar fingerprints and reconstructing timelines. To see if Caldwell 51 actually fits this expected profile, we have to treat the galaxy kind of like a crime scene and analyze its stellar fingerprints. Using data from over 165,000 resolved stars, astronomers put together a color magnitude diagram. By pushing Hubble's cameras to their absolute limits, they were able to reach all the way down to the oldest main sequence turn-off stars. Because the data captures these incredibly faint ancient stars, it gives us an unprecedented time resolution of about 1 billion years. We are peering deep, deep into the galaxy's ancient past.
By charting the luminosity and color of these stars into distinct regions, like the prominent red clump and the main sequence, researchers can quite literally map out the exact age and metallicity of the entire stellar population. It's a lot like reading the rings of an ancient cosmic tree.
And wow, the resulting 3D star formation history derived from that data reveals something absolutely incredible. You can see a flat, steady landscape. You're looking at continuous, ongoing activity across age and metallicity over the last 14 billion years. There is absolutely no massive spike at the beginning of its timeline like the models predicted.
Which brings us to Section 3, a constant cosmic engine defying expectations.
The contrast here is just stark. Instead of a massive burst of stars at the dawn of the universe, which remember is what the overcooling models expect, the reality is that Caldwell 51 has been steadily and constantly forming stars for its entire existence. To put that into perspective, the star formation rate has varied by at most a factor of 2 from its average over the entire lifetime of the galaxy. That is just wild.
This insight actually echoes a foundational observation made by astronomer John Gallagher way back in 1984. This is the true aha moment of our explainer. The data firmly confirms that our classic theoretical models simply fail when they're applied to irregular dwarfs like Caldwell 51. The simple, closed-system models just cannot account for this constant cosmic engine.
Moving to Section 4, our local group outlier, a star-forming rebel.
Now, this naturally raises a huge question. How on earth has Caldwell 51 managed to keep this engine running for billions of years without running out of fuel? Well, to answer that, astronomers had to look beyond the visible stars and peer into the galaxy's invisible outer halo, known as the Circumgalactic Medium, or CGM. Using 10 different sightlines with Hubble's Cosmic Origin Spectrograph, even looking at background quasars, they detected gravitationally bound metals like ionized silicon and carbon. Basically, they discovered a massive reservoir of gas right there in the halo, being constantly enriched by ongoing stellar outflows. And the real secret to maintaining this gas reservoir, it's all about location. Because Caldwell 51 is so isolated on the very outskirts of the local group, it hasn't had its gas violently stripped away by gravitational encounters with massive galaxies like the Milky Way or Andromeda. This perfect isolation allows the galaxy to act as an incredibly efficient, self-contained recycling engine, retaining its outflows and feeding that constant rate of star formation.
You can actually see this perfectly represented in the data. Notice the solid black line charting the cumulative mass fraction of Caldwell 51. It's a steady, constant climb upwards over billions of years. Now compare that to the red lines. Those represent the theoretical models plunging right into the overcooling trap, forming all their stars way too early. Caldwell 51 completely dodges that trap. It's a total rebel.
So, as we wrap up this explainer, I want to leave you with this final thought. Caldwell 51 is just one tiny, blue-shifted outlier out there in the Cetus constellation. Yet its steady 14 billion-year heartbeat proves that our absolute best computer models still have massive blind spots. If our cosmological models are this wrong about an isolated dwarf galaxy, what else about the dawn of the universe are we fundamentally misunderstanding? Keep that question in the back of your mind the next time you look up at the night sky. Thanks for exploring with me.